Number 1. Researchers in a sleep lab at a college decided to see how a night of no sleep affected the ability of volunteers to answer 50 addition problems in a minute time span. 30 volunteers were randomly assigned to two groups. Group 1 was not allowed to sleep and Group 2 slept normally. The results, in terms of questions answered correct out of 50, are given below. So I have these two groups here, and Group 1 did not sleep, Group 2 slept. And I want to know what's the difference in means. What's the difference in means between these two groups? So hopefully what you did is you took Group 1, and to find the mean, you threw it into L1 in your calculator, did 1var stats, and got the mean for Group 1 was 26.3. So Group 1 on average got 26.3 questions correct. Whereas Group 2 on average, the people who were allowed to sleep, got 32.6 questions correct. So to calculate that difference in means, let's do x bar 1 minus x bar 2. Well, if I do 26.3 minus 32.6, I'm getting negative 6.3. How do I interpret that difference of means? Well, that difference means the average for Group 1, the sleep-deprived people, the average for Group 1, the average score for Group 1, I should say, the average score for Group 1 was 6.3 questions less. The average number of questions for Group 1 was 6.3 questions less than the average number of questions correct for Group 2. So the key thing is that Group 2 did better. Group 2 got 6.3 more questions right. Their score was 6.3 higher than Group 1 because that difference was negative, which means Group 2 was bigger. Re-randomization was done 250 times. We need to know that that process of re-randomization means that I take the data, I scramble it up, make two different groups, find the means. Take the data, scramble it back up, find the means, find the difference. Take the data, randomly assign to the two different groups, find the difference in those two groups means. That's what re-randomization does. When we re-randomize, we assume there's no difference. When we do re-randomization, we assume there is no difference. Which is why our dot plot or histogram is going to be centered around 0. On the distribution below, mark our difference. So we had a difference of negative 6.3, which I'm going to say is about, I shouldn't use blue, is about right there. Estimate how many differences of the 250 were just as extreme or more extreme than our difference. Well, 1, 2, 3, 4, 5, I'm going to say 6 were. 6 simulations had a difference that was more extreme or just as extreme as our difference. Is there statistical evidence to support the researchers' claim that the difference between the two groups is significant? Well, what's the probability of getting a diff that's less than or equal to negative 6.3? My difference was negative 6.3. I want to know what's the probability that it's less than that. Well, that probability comes out to be 6 out of, there was 250 re-randomizations. 6 out of 250 is 2.4%. So is there statistical evidence to support the researchers' claim? The answer is yes, there is statistical evidence because assuming there is no difference, the probability of getting a difference just as extreme or more extreme than our difference is 2.4%. That is not a likely outcome. So assuming there is no difference, the probability that the difference is negative 6.3 or more extreme, just as extreme or more extreme as negative 6.3, so I'm smaller than negative 6.3. Assuming there's no difference, the probability that the difference is negative 6.3 or more extreme only occurs 2.4% of the time. So there's a 2.4% probability of getting a difference that extreme based on the simulation. Because the probability that our diff is less than 5%, it's less than 5%, we can say it's statistically significant. statistically significant. Statistically significant. That means it didn't happen by chance. It did not happen by chance. This difference did not happen by chance. By chance. This difference did not happen by chance. So we found our diff value, marked it on the simulated distribution, and then because there was only 6 out of 250 less than that, we assuming there's no difference, the probability that the difference is negative 6.3 or less occurs only for 2.4% of the time. Because that value is less than 5%, we can say that that difference value is statistically significant, which means that it didn't happen by chance. There was something else going on there, and it happened to be sleep deprivation in this case. Can we conclude that a night of no sleep caused this difference? The key word there is caused. To have a causation, we need an experiment with random assignment. Well, did we have an experiment with random assignment? Yes, we did. So we can say it caused. We can say there was causation. Yes, we can say there's a causation here because it's an experiment, number 1, with random assignment. Number two is a Regents question that I was not entirely a fan of, but so I threw it on the homework instead of putting it on the test because it's a better homework question to talk about. Ava designed an experiment to determine the effect of a new energy drink on a group of 20 volunteers. 10 students were randomly selected to form Group 1, while the remaining 10 made up Group 2. So she's doing an experiment here. Each student in Group 1 drank an energy drink, and each student in Group 2 drank one cola drink. 10 minutes later, their times were recorded for reading the same paragraph of a novel. The results of the experiment are shown below. So there's Group 1, they got energy, Group 2 got cola. Ava thinks that drinking energy drinks makes students read faster. Using information from the experimental design or the results, explain why Ava's hypothesis might be incorrect. Well, what I have a problem with her experimental design here to say that energy drinks cause them to read faster is we have no control group for when they don't drink energy drinks, for when they do not drink energy drinks. It would have been nice to get people's times if they didn't have energy drinks and they just read the paragraph. That way we could actually compare, did the energy drink cause them to read faster? Another error that this was not obvious to me at first, this is an example that New York State gave as a response was, if you look here in Group 2, that guy read really fast. That guy also read really fast. Those times are actually both quicker than all the times in Group 1. So Group 2 had times that were faster than Group 1. So that's more talking about the results, but I think the experimental design piece is a crucial flaw in her experiment. She should have done energy drinks and no energy drinks, not cola. But anyway, let's continue on. Using the given results, Ava randomly mixes the 20 reading times, splits them into 2 groups of 10, and simulates the difference of means 230 times. So she's going through that re-randomization process of take the data, throw it in a bin, split it into new groups, find the difference. Plot that point. Take the data, re-scramble it up again, set it into 2 different groups, find the difference. That's what Ava's doing here. That's that re-randomization process that she did to make this distribution. Ava decided that the difference in mean reading times is not an unusual occurrence. Support her decision using the results of the simulation. So we need to find our difference in means. What was our difference in means? And I'm going to do Group 1 minus Group 2. Our difference in means comes out to be what? 17.7 minus 19.1. 17.7 minus 19.1. That's a difference of negative 1.4. So our difference value in this case is negative 1.4. That's the statistic that we're working with. So we find that statistic on our distribution. We find that statistic on the distribution here. That's negative 0.6, negative 0.5. I'm going to say that's negative 0.4, let's say. Let's say there's my cutoff. So how many values were just as extreme or more extreme? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 22, 23, 24, 25, maybe 25 of them. It doesn't really matter if you include that at this point, because that's 25 out of 203. The probability of getting a diff less than or equal to negative 1.4 for this distribution is 25 out of 232. And if you divide that out, we see that we get a percent that's definitely much bigger than 5. Let's get that actual percent. 25 divided by 232 comes out to about 10.7%, 10.8%. So that probability is much larger than 5, so it is not an unusual occurrence. It is not statistically significant. That difference of negative 1.4 could have happened by chance. So support her decision using the results of the simulation. So assuming there was no difference, between the groups, the probability of getting a difference extreme or more extreme than negative 1.4 is 10.8%. So assuming that there was no difference between these two groups, the probability of getting a difference of negative 1.4 happens about 10.8% of the time. This value is bigger than 5%. This probability is larger than 5%. So it is not unusual. So it is not unusual. Unusual. Instead of saying it's not unusual, we could have said it was not statistically significant. Not statistically significant. Or we could have said it could happen by chance. Getting a difference this big could happen by chance. So the key steps for working with these difference of means is you find your difference of means, you find the difference between those two groups, plot it on the simulated distribution that's given to you, probably done by re-randomization. So we assume that there's no difference. What's the probability that we get a difference that extreme or more extreme? I counted 25 out of 232. 25 out of 232 gave me a 10.8% probability. That number is bigger than 5%, so this value is not statistically significant. That difference value is not unusual, it's not statistically significant, which means it could have happened by chance. It could have happened by chance.